Hi, and welcome to episode 3 of Cartography. And with me today, backed by popular demand, again, is John Nelson.
Hello!
And Edie Punt is also back.
Hello.
And I'm Ken Field. And so we're going to spend a little bit of time in this episode talking about the language of graphics and the way in which we prepare all of the little symbols that we put on the maps, the choices we make, all of the minutiae that we get involved in to make a map really sing.
Yeah, good.
Sounds good. Let's do this.
So we spoke a little bit in episode 1 about the language of cartography, and I used the word graphicacy.
Graphicacy?
Yeah.
Graphicacy.
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 And so what does that entail? What are the real nuts and bolts of making decisions about how you draw lines and points and areas on a map? Let's deal with generalization first as a broad theme.
Yeah, well, generalization really comes about because you simply can't fit everything into the map. If we're mapping the world, people talk about what would a 1-to-1 scale map look like. Well, it would cover everything.
Like a global map, if you were just to crunch highly precise data down into a global map, you'd have these busy coastlines that distracted from the overall shape. And so that's something that I see commonly.
Yeah.
It's an ungeneralized global map.
Yep. And it's not always just simplification, like simplifying what's there. Sometimes you need to exaggerate things, like make them bigger than they would be to make sure they get included. So to use the coastline example, if an island is important, maybe it's got to be slightly bigger.
Are you suggesting we lie with maps?
See, it's all about communication, John. What's the message of your map? What are you trying to convey with this map? And then you need to make choices. And generalization is really a big toolkit. There's a bunch of different methods you can use, and you gotta pick the right one, keeping in mind with what you're trying to say with your map.
Essentially, really what it is most data is collected at a fairly large scale. It's often survey data, so you have very, very detailed data sets. And you might want to make a map that's really only maybe, 10 inches by 8 inches. And you've got data for the whole world. So just dumping that on the map is going to create a real problem. Graphically, It just doesn't look right. In fact, I remember one of the first hand-drawn maps I made. We were told, draw the map at twice the size. Use a thickness of line, twice the thickness.
Ooh.
Or even 3/4 or 75% increased. So you do your line. And then the trick is that you then reduce that, and it tightens up all the line work and looks beautiful, because you can't draw that accurately at that actual scale, but you do it double the size. And then, so that's kind of part of generalization.
The important thing, though, you mentioned, your data is usually at large scale. It's really important to understand you cannot go the other way. You are implying precision that's not actually there in your data anymore.
Right,
so
and the person
really
reading
careful.
the map is going to read it as if it is a correct.
Exactly.
Sure. Yeah. Thankfully, we can use a lot of software tools to actually perform a lot of those techniques for us. Also within the language of graphics is how we use different aspects or components or parameters of the graphics to play on the way in which our eyes and our brain work. These are broadly called visual variables or retinal variables.
That's the neat stuff from the 50s and 60s where psychologists were measuring our responses to stimulus and how we actually interpret them.
Yeah, and
it's not always true.
If a cartographer is going to make a great map, it's really useful to understand how somebody else's eyes and brain are going to interpret what you make. So there's a whole load of them. Let's maybe pick a few and go through. So do you want to throw one out there and we talk about it?
One of the obvious ones is size, for sure.
Right.
And there's different ways of showing size, right? So there's the relative height of something, which turns out we're pretty good at measuring how tall something is, looking at it and going, okay, that's a lot taller than the other one. And
yeah, well, and then that's 1 dimension. 2 dimensions is area. That gets a little bit trickier. It's not as easy to tell when a circle is twice as large as another circle. That's a little bit trickier.
Yeah, and what about if we go 3D and put some volumetric?
it's the worst.
Yeah.
We're terrible at that.
Don't do
We're
that.
terrible at volume.
Human beings are really bad at estimating volumes.
It
from
looks
symbols.
kind of cool, but it's hard to judge.
The basic component is actually humans are very good at seeing what is smaller in size.
Bigger means more of something.
So what else?
know?
Color?
That's how we process it, though. It's
Hue,
more,
color?
less and more. You're going with color.
Yeah, can you
Well,
You can attach color to a visual
Yeah,
variable.
colour's an awkward one because
Yeah.
actually colour is not a single component.
Yeah, what are the components of color?
So we can think about hue, which is what we think of as what? Red, yellow, blue, dominant wavelengths.
Yeah.
Value, or lightness, and chroma, or saturation. So let's deal with hue first and how
Yeah.
that works.
Often hue is, they're, different but equal.
Yeah.
And so that's what we use for our nominal data, meaning we want to show different things, but one's not more or less than the other.
Qualitative scheme.
Right.
A qualitative.
Yeah,
So,
qualitative.
so if you compare how our eyes and brains process hue in terms of it being different to size, it's less and more.
Yeah.
Whereas actually hue is just different. But maybe if we picked a single hue, let's say a beautiful orange,
Yes, lovely.
Oh, nice.
Thank you.
Yeah.
and let's change its value.
Yeah.
So let's go from a really light orange to a dark orange.
I would look at a map, as long as it's a light base map, and the light orange I would think of as representing less, and the dark bold orange I would think of as representing more.
Suddenly we're using color now to apply to quantitative data
Yeah.
Yeah, less and
instead
more.
of qualitative.
And if you
with
put
the
it
hue.
if you put it on a dark background, then maybe it's inverted. Maybe that sort of
the light becomes bright.
yeah, exactly.
Yeah. And the
Contrast
dark-
drives meaning.
Yeah.
Yeah.
This is contrasting from the background, so it must be more.
Another one we throw out is shape. Shape is a good visual variable. So, a triangle is different to a square, is different to a circle.
Yep.
And if you put 3 different shapes of the same size in front of somebody, what are they going to see?
If you stick to the simple geometric shapes, we can be back in that where it's different but equal. If they're too detailed, you can argue that a triangle is more complex than a circle. But then if you go even further into really mimetic shapes, so shapes of symbols that look like the thing that they're representing.
Like a cow or a chicken.
Yeah, yeah.
Or like a mug. Yeah.
Yeah, but you have to be careful there because there are different connotations across cultures, across languages.
And it looks pretty ugly quickly. Right?
Yes.
So there's a warning there, and that if you've got a literal point item, restrict yourself to just a handful or less.
So I think the key with these visual variables is it's like the cartographer's palette. It's their, you sort of pick from different things to mean different things on your map.
Can you combine them?
And you can combine them. And this is where it gets kind of complicated. That's where the art of cartography, I think, comes in. It's, you might have a circle, but then you might change its size, and then you might change its hue, and then you might add a little bit of lightness in there. And if you're John, he would probably throw a load of transparency in there. John, a lot of your maps actually use transparency pretty heavily. Do you want to explain
They do.
the reasoning?
I like to use transparency with raster layers to help suppress parts of the data that are less important. Maybe the reflective side of a mountain is more important and the shadow side is more important, but the gray values in between, I'll just go ahead and suppress that with transparency. From a data value, I like to use transparency for time-based data. It seems like a natural mapping to me, and I've seen some effective maps like this where older elements are more transparent, they kind of fade off, which is kind of a nice natural mapping because that's how our memory works in a lot of ways. You've got something very opaque, which means it's recent, and then it fades off into increased transparency over time.
I think transparency is one of those things that where cartography has gotten more exciting with technology, because transparency was really hard to do photomechanically.
Yeah.
Yeah, I think one of the best ways to test whether all of your visual variables are working together is, can you make a good legend out of it? Because a kind of less good legend just lists all of these symbol variations in isolation. But really, that's not how people are looking at your map. They're looking at certain symbols that are sized this way and colored this way and oriented this way. We didn't talk about orientation.
No.
Is all of this working? Because if you can't make a sensible legend out of all these things you've mashed up together on your map, that's a really good sign that nobody's going to be able to interpret it.
Just forget the legend for a while. Even ask somebody, look at this map. What do you see? What do they tell you? What's the key message that they get without the legend? The legend should be there as a support, it's there as reference.
If you're using a visual variable, try to tie that to a natural interpretation of that. So orientation. If we have a symbol and it's angled a certain way, the easiest way that a human will interpret that is literally it's pointed in that direction. So if you've got a hurricane path, you would use angular symbols that indicate which direction it's headed at that point.
Well, we're good for some talking points on language of graphics.
Yeah.
So this week's map of the week is another oldie.
Map of the week.
We're picking a lot of oldie maps, but they're great. They're classics.
Yeah.
A little bit good.
It's the classic map of cholera in Soho in London, 1854.
Jon Snow.
John Snow's map.
Which invented epidemiology.
Well,
it did.
it
Let's
did.
just say it.
Yeah. So this guy was a genius. He was an
Absolute
statist.
genius.
So this map was, I think, really the first to sort of look at health and health phenomenon in a spatial context. So really what it's about is they were trying to figure out why people were dying of cholera. And so he started mapping just with a simple black stroke on a black and white map where the deaths were occurring. And he was the first to think about, let's look at the spatial pattern of where they live. And once he did that, it was pretty easy to see that most of the deaths were centered around a particular water pump.
Yeah.
And they figured out that it was the contaminated water source. Something that was interesting about that map is there were areas near that single contaminated pump where there were no deaths. So is it this contaminated pump? So why aren't there deaths here? Well, when they dug a little further, they found that in those buildings or businesses, they had a separate water supply. So,
Also, one of them was the employees of a brewery,
Yeah.
which killed cholera. Once again, beer saves the day. Beer saves the day.
Yeah, because
Cartography helps
all the
illustrate
workers
that.
were allowed a pint of beer.
One element
more.
that's often overlooked in this map and not talked about a lot is another dimension of data that Jon Snow used, which was he suspected maybe it was these pumps. And he constructed essentially a Voronoi diagram or a Thiessen map, creating areas around these pumps to really hone in on the areas.
which
that-
pump each person was most likely to go to.
Right.
So it teaches us a lot about how we use graphics to tell a particular story. So that's John Snow's map, 1854. Our map person this week is Jacques Petain.
Yeah.
Jacques.
So this is maybe a name that
Information.
strikes fear into people because this guy wrote this book, 1967. This is one of the sort of Bibles of information visualization. Jacques was an academic and spent a lot of his career investigating, the science behind how we interpret graphical marks.
He's one of the guys doing the cool experiments in the 50s.
Exactly. And he wrote
Smoking
it.
cigarettes, wearing a lab coat.
They were just rumors.
I don't know if you did
But
those things.
he wrote it up as a textbook, and it's a monster. But it's
Full monster.
the most detailed description of all of this stuff that we've been talking about for the last few minutes. If you want to know exactly why something's going to work or how it's going to work, then this
Ask
guy
Jacques.
has actually
Yeah.
written it up.
This book really goes through all of these permutations that we've been talking about how data and quantitative data can be described with the communication of maps. And, really this is information communication that he's talking about.
Yeah.
But it really applies itself to cartography.
And still relevant today as it was when he originally wrote it.
Yeah.
So Jacques Petain, well worth a read. This week's tools of the trade, drum roll again. Let's go into the
Toys.
magic toy box. Let's see what we've got, shall we? I've got actually one for each of us this time.
Oh, great.
How about that?
Toys.
So for John,
Thank you. That's appropriate, too.
yeah.
8 colors.
And,
That's more than you usually use.
And for Edie, what is this?
I like it.
And for me,
I'm not going to lie. I'm a little bit jealous
No, you got 8.
that Edie got this.
for me, this little box of magic. So let's start off with the crayons, John.
Okay. Tools of the trade. You know, I actually have not made a map with crayons. If you're making a map that has more than 8 colors, there's a pretty good chance that your readers aren't differentiating between them very well. So 5 plus or minus 2.
Edie, what have you got there?
Looks like maybe a weapon, but it is actually an ink pen. Do you know how this works, John?
No, I don't.
So there's 2 prongs and a screw that brings those prongs closer together or farther apart.
Does it clench something in its
Yeah,
jaws?
so you can actually you can trap a small blob of ink in there.
You might want what's in this box.
Ooh, that looks modern.
By
to
these
this,
standards, it
yeah.
is. This is called a pen.
Yeah. Oh, look, there's a giveaway right there.
Yeah.
Yeah, tells
So-
you how to hold it.
That's how
Yeah.
one holds this thing?
Yep.
You can unscrew the cap, and it has
Oh
a,
my goodness, look
a
at that
really
point.
super fine point
That's
of
incredible.
0.2 of a millimeter.
Yeah.
So you're taught to hold it vertically, and that's how you draw.
Yeah, because that one you can put a fair bit of ink in and maybe get through most of your project.
so
This
you'd be-
one has to be refilled.
Be much more productive with this guy.
Yeah. So it puts it into perspective about choosing a line width in software and then deciding you want to change it to something different.
Pick up a different pen.
Yeah, back in the day, you really had to commit to those line
You had a lot of
widths.
invested into your materials.
Yes, definitely. Tools of the trade.
So there's a lot of ways that you can get your graphics correct, okay, in the language of graphics, and following sensible syntax and doing sensible
I like how you
things.
said that. There's a lot of ways to get it right.
Yeah.
But there's occasionally a few things that you can do wrong. So maybe we want to call those part of our carto fails
Okay.
section or our pet peeves.
Yeah. Things to avoid.
Have you got a
Yeah.
thing that...
Just think about it. Everything you're adding to your map or to your symbol or to your surround is competing for attention and taking away some of that light that's going into your eye. So,
And also the use of like solid black.
yeah.
Try to avoid solid black and go dark gray.
Yep.
And you'd be surprised by how light gray you can actually get and have it appear to be relatively.
I have, is kind of the inverse of the too much black, is too much colour. And I see a lot of maps that use a sort of a spectral colour scheme, or maybe we might call it a rainbow colour scheme.
The rainbow.
And we've already spoken about what different hues mean. They mean difference. Like yellow is different to red, is different to blue, is different to green. We might use blue for water, green for forest. But you see a lot of scientific visualizations, particularly where they go across the full spectrum of color in this all its magnificent rainbow glory.
Applied to a less is more range
Yeah.
of data, right?
Yeah. And cognitively, actually, that's really difficult for people to interpret. Why should red be more than blue, or more than green, or less than
Right.
yellow, or bigger than purple, or smaller than pink?
This-
There's often, almost certainly, a better choice
Yep.
than using a rainbow color palette. My biggest pet peeve
Of all.
ever.
Of all of them? Out of all of them?
All of
yeah,
them.
Okay.
yeah, and this is about representing data on a choropleth map.
Yep.
And in a very simplistic way, you always need to show your data as a ratio or a proportion or a percentage or per capita or some
need
derivative of
To
a total.
normalize your data.
So don't map raw totals.
Yeah. So the example I want to demonstrate is, you've got your data. Let's say it's a map of the United States counties,
Sure.
and you've got a range of data, some small values, some large values,
Yep.
and they're totals. Okay.
Just raw totals.
Raw totals of numbers of people. So,
Okay.
so let's kind of have a little physical experiment about
Visuals.
Yeah,
Yeah.
look at this. So I've got a pot of liquid here,
Okay.
and I'm going to measure out the same total, and hope that I don't spill it. Okay, this is a measure
Okay.
in this glass here,
Yep.
and I'm going to pour out the same measure into this glass. Spilt it. It's okay, it doesn't matter. And let's go for this final one.
Okay.
I didn't work as a barman very long, obviously. Now, the interesting thing is what happens when you look at these areas from above. So this is a glass with a very small area, surface area. This is actually a glass with a hexagonal shape. It's an odd shape. And then this is a glass with a very wide bottom, and it's got a big surface area.
Yep.
So when you look at these glasses from above, you'll actually see that this green liquid
Yeah.
is darker here,
It's very dark here.
much lighter here, and this middle glass takes on a middle value. Yet they're the same totals. So the point here is that when you're pouring data into your polygons, into your areas, and they're the same totals, actually the area is going to modify how they should be seen. Or maybe the population total is going to modify how that data is seen. You might have a large area with only 100 people in, and so one person is 10%. You might have a very small area with 1 million people in, and what's 1% of that? But it's a larger total than this one.
Right.
So it's about creating a visual balance across all your areas, and you have to accommodate the problems of geography and different population totals by processing your totals into some derivative, a ratio,
rate.
a proportion, a rate, percentage.
So normalize it.
So normalise it.
Normalize
Yeah.
your choropleths.
So I think with that, we're pretty much done with the Carto fails, and I'd ordinarily offer you a biscuit, but would you like some strange green liquid instead?
Oh,
Green liquid.
Yeah, let's normalise your choropleths. Cheers.
cheers.
Food coloring down the hatch.